Hey everyone, Professor Dustin here, and I'm going to talk about rotational dynamics in this video. So recall linear dynamics. This is basically an application of Newton's second law where you add up all the forces and you get mass times acceleration in a vector sense. So all the forces in the x and y directions, the acceleration in the x and y direction. If you know all the forces, you can then find the acceleration. If you know the acceleration, you can use the kinematic equations to find the position and velocity of the object at any time. That's basically the dynamical problem. Given forces, how do you figure out what the motion of an object is? Well, now we want to do the same thing, but for rotations. For objects which are extended, that is not point-like objects, but have some forces acting at various locations on the object, creating torques. Well, luckily, all we really have to do to do this is translate between the linear quantities that we see in linear dynamics into the rotational quantities that we see in rotational dynamics. So here is the translation. On the left-hand side here, I have all of our linear quantities: force, mass, acceleration, position, and velocity. And on the right-hand side, I have their corresponding rotational quantities. So the first one is torque. Recall that we can also write torque in terms of forces as R cross F. We have mass turning into moment of inertia. Recall that the moment of inertia for an extended object is normally something that we can look up in a table somewhere. Our acceleration now becomes angular acceleration. The angular acceleration typically has units of radians per second squared. Our position now becomes simply angle. Typically that has units of radians. And our velocity becomes angular velocity. And as you know, that typically has units of radians per second. Well, so now we can take these three equations, the sum of the forces, the x, and the v, and turn them into rotational equations using this translation. The sum of the forces is going to be the sum of the torques now. And our mass times acceleration will simply be our moment of inertia times our angular acceleration. If we want to write down the position as a function of time, we just have to use our translation here. Position is going to be angle theta, 1/2 at squared, 1/2 alpha. And t is going to be the same. There's no difference between a linear t and an angular t. It's just the seconds on a stopwatch. V is going to be omega, so this will be plus omega times t. And x naught will be the initial angle, plus theta naught. To do our velocity, we want v is going to become omega. At will be alpha times t, angular acceleration times t, plus omega plus v naught, which is going to be omega naught. So this set of equations now is going to describe the rotational dynamics problem. It exactly follows the linear dynamics problem, that is, find all the torques, add them up, set them equal to the moment of inertia times the angular acceleration, and then find the angular acceleration. A lot of the effort will be put into finding the angular acceleration. Once you have the angular acceleration, simply using the position or the velocity formula in the angular form is exactly like doing the kinematic equations. You have to figure out which of these things you know, which you don't know, and how can you find the stuff you don't know. Okay, so that's an introduction to rotational dynamics. I hope this has been clear and helpful. Thank you guys for watching. I will see you next time.